In Lesson 2.2, you're going to be working with the review box to begin with. They give you a rational function, which has one factor on top, and then it has three different binomials down below. Now notice that the power of the binomials are 1, 2, and 3, meaning that x will be to the fourth power. Correction, x will be to the sixth power. The first thing you want to do is find the wholes that exist. So the whole is going to have a value where the top and bottom factors are the same, and that's going to be when x equals 1, and that's why we have the 1. For even vertical asymptotes, your vertical asymptotes are going to be located wherever the denominator factors are unique, or wherever the denominator factors are not repeated in the numerator. We have two of those. One of them is even, one of them is odd, not really because of the exponents, but because if we use the even and odd properties, then by testing them against their symmetry to the y-axis and to the origin, we discover they're even and odd. But as a general rule here, we can claim that this is even and this is odd. We have a vertical asymptote at x equals 2 and a vertical asymptote at x equals 4 for the even and odd vertical asymptotes. Now those vertical asymptotes are going to have specific behaviors around them as the function approaches them. You can never pass through a vertical asymptote, unlike a horizontal, which you can. And it's like a seawall with a wave hitting it from both sides. Either that wave will head toward infinity from both sides or negative infinity, in which case we say they're even because they're both heading in the same direction. Or the waves will go in opposite direction, and if they do go in the opposite direction, we say they're odd. So how do you know which way they're going to head? Which of these situations will occur? Well, we use something called sign analysis. And in sign analysis, we're going to check the rational function to see whether the numerator and the denominator have different signs or the same sign. And a good example of that is example number 3. Example number 1. If you look at example 1, we're trying to approach 2 from the right-hand side. 2 is going to be my vertical asymptote because we see this factor only occurs in the denominator. So with a vertical asymptote at 2, let's approach it from a value greater than 2, such as 2.1. Pick something fairly close to 2. I wouldn't suggest picking 3 or 5 or 8. Pick a number that's usually one decimal place. If I pick a number greater than 2 down here, then I'm going to end up with a positive value. If I pick a number that's greater than 2 here, this will also be positive. So I end up with both positives, which means that I'm going to have a positive positive, and I'm going to have positive infinity that I will head to. Now the 5 and the 0 designate what happens if you directly substitute. And as you can see, 5 and 0 give us an indeterminate form. That suggests that we're going to have either infinity as an answer or does not exist. Have a look at number 2. We're approaching the same vertical asymptote from the negative side, the left-hand side. So I'll pick a number such as 1.9. Now 1.9 is going to be less than 2 here, so this number will end up being negative in the denominator. And a 1.9 and 3 here gives us a positive value. And because we end up with negative overall, and because this is going to be a vertical asymptote approach, then we're going to end up with a situation such as this one here or this one here. We're heading toward negative infinity. As I look toward 3, I see that I've got a limit as we approach 1 from the right-hand side, and that's a vertical asymptote. So we're going to have infinity as our answer. As we look at the right-hand side, we go ahead and pick a number greater than 1, such as 1.1. Now 1.1 minus 1 is going to be positive. Regardless of whether it is or not, it has to be positive because we square it. So we end up with a positive in the denominator. Up here, a negative, or a 1.1 rather, minus 2 will be a negative number, and I'm going to end up with a negative. So because I have a negative and a positive, I'm going to end up with negative infinity. How do I know it's infinity? Because when you have vertical asymptotes, as you approach from both sides are either going to head toward negative infinity or towards positive infinity. On number 4, we have a vertical asymptote at 1. We're approaching 1 from the negative side, the left-hand side. So I pick a value less than 1, such as 0.9. If I put 0.9 up here, I'll end up with a negative number. If I put 0.9 down here, I'll end up positive because it's already squared. So I have a negative over a positive. Remember that vertical asymptotes always have a limit of infinity, so I end up with negative infinity from the negative and positive right here. Number 5 is the same process, but we can factor and clean this up. So I factor out x squared minus 4, and I've got these two factors, and x minus 2 down below give me a whole right here. I'm left with x plus 2, and because I'm heading to 2, I can then go ahead and substitute directly into the remaining factor to get my answer of 4. But I do have to note that there is a hole in the graph at 2, 4. When you're heading toward infinity, then the phrase infinity and beyond comes into play. And in this case, I'm trying to head out toward the extremes of the x-axis. So I'm heading toward infinity to the right, negative infinity to the left, and I want to see what the behavior of the function will be. Now, either the function will level out at some point, which leads to a horizontal asymptote, or it won't. You may end up having 2 different horizontal asymptotes or just 1. In between those extremes, my function can do just about anything it wants, depending on the function. As we look at number 6, this is where we're going to use the n and m rules. And in this case, n and m are the same, so we use the coefficients. 5 over 10 is 1/2. That's going to be the vertical asymptote as I head toward infinity. As I look at number 7, I use the n and m rules. M is greater than n, and so this value heads toward infinity, this value stays less, and I end up with the whole fraction heading toward 0 because the denominator is greater. On number 8, we use the same rule. There is no horizontal asymptote in this case, and the reason why is because as we look at x to the 4th, it's greater than x to the 3rd, so the numerator dominates, which means that as I head toward infinity, this value grows infinitely large over this one, and I'm heading toward infinity overall. I could say there's no horizontal asymptote, or I could say that the limit heads toward infinity. For number 9, the answer is 1/2. For number 10, it's 0, and number 11, again, I have does not exist, which is the same as infinity. Now, a note about number 8, you could have also written that the answer does not exist. I prefer to write both answers to show the grader that I understand exactly where I'm headed toward. For number 12, we're going to have to expand this out a little bit. So 2x to the first power times x to the second gives me 2x to the third. And x to the first times 3x squared is going to give me 9x times x, or 9x cubed. Now I can use the n and m rules. X cubed over x cubed is 1, and I end up with 2/9 as my limit. The key is this note right here. When you look at the examples down below, you can see that in this case, the 4x squared dominates, the 3 really doesn't come into play, and the square root of 4x squared gives me 2x. I use absolute value here to take into account the positive and the negative in front. Then I divide by x, and when I do, the x's both turn into 1, and I end up with 2 as my answer. Even though we're going to infinity, we're heading toward a horizontal asymptote. Another thing to note about this is that as I go to greater and greater positive numbers, this value right here will be positive, this value will be positive, and so my 2 ends up as a positive sign check, and I end up with a positive 2. When I do the same thing to negative infinity, or heading in this direction, then I'm going to use a value here that will always be positive. However, the value here will always be negative. Therefore, I have a positive over a negative, positive over negative, and I end up with negative 2 as an answer. Now you're ready to do the homework problems from assignment 2.2. Good luck.